PIs, let's get started with our fun BAIOSPHERE AI in the Bavarian ecosystem session. So there's a tradition at our HAICONs that we always add sort of one session where we describe how the local ecosystem has been composed, what people do, and then have a series of, I would say, high-profile speakers from a local environment. I'm very excited to listen to them. Because Munich is so big that, quite in fact, you actually don't listen to their talks all that often. But before we start with the scientific parts, very excited to welcome Michael on stage. We have been working together in this organization system for the Bavarian ecosystem, the BAIOSPHERE, as we call them. And I think we have a slide for that, for the BAIOSPHERE, if you could put that up, which is our Bavarian AI ecosphere. And Michael is organizing this really with a lot of effort. Very grateful for pulling us together. You know how hard it is to shepherd scientists. And I would leave the stage to you. Thanks for coming.
Thank you, Fabian. So I'm the local guy, and I'm going to introduce the locals who act on a very global and international level of excellence, of course. And this session is called AI Research Across Bavaria. And as you might know, BAIOSPHERE is the network that is connecting AI in Bavaria, from research to industry, the innovation ecosystem, policy, society. And the goal is, of course, to present Bavaria as a leading ecosystem in Europe and in the world. Since the launch of the high-tech agenda in 2019, the Bavarian state government has invested quite a lot in this place. 130 new professorships have been installed here. There are more than 90 AI-related study programs at our universities and universities of applied sciences. It's literally tens of thousands of students in this field now, so this is also a promising outlook to the future. And Bavaria is not only academically strong, but it's also a very, very strong place for the startup ecosystems. According to EY, just last year, 3.3 billion of euros have been invested in Bavarian startups alone. This is really a top rank amongst the top three probably in Europe. And if you've seen the last Financial Times ranking, the top 10 innovation hubs across Europe, the first three places go to Munich and Nuremberg also, and number 9 is also in Bavaria. So why am I telling you this? Not to just boast, but to tell you what great place this is here, what great colleagues you have, and how awesome it is to contribute to all of this. This session will showcase outstanding AI research from across Bavaria, AI research in medicine. A few practical announcements. If the room gets full, you can also see the live transmission of this session in the Gern stage. And after the session, all the speakers are available in the networking area up there. There's a speaker's corner, and there will be lunch served, so you can talk and mingle with all of them afterwards. This having said, it's my great pleasure now to introduce our first speaker, Daniel Rückert, one of the world's leading researchers in AI for medicine and medical imaging. He's an Alexander von Humboldt professor at Technical University in Munich. AI in medicine and healthcare is his chair. He's one of the 4 directors of the Munich Center for Machine Learning in Munich, a German research center of excellence. He's also a professor at Imperial College in London, and just last year he was awarded the German Leibniz Prize and became a fellow of the Royal Society in the UK. His talk is entitled AI and the Future of Medicine. Please give a hand to Daniel Rückert.
Thank you, Michael, for the very kind introduction, and Fabian for organizing this great event. I think it's fascinating to see so many people doing AI research here in one place, coming together from all across Munich, and also, of course, from all over the world. So I wanted to talk to you about how I see AI and the future of medicine. And you've already seen that, of course, there's tremendous amount of progress in AI transforming all areas of science. We have seen these 2 Nobel Prizes. It's now just over a year or 18 months ago that 2 Nobel Prizes effectively were given for contributions which AI developments made in science. And if you look at what happened a couple of weeks ago, these 3 papers all appeared at the same time, I think on the same day, in Nature, showcasing how AI is really transforming the science of discovery and how we do things in all aspects of science. And that's also what this conference is all about. Now, I wanted to focus a bit more specifically on one field, one scientific discipline in medicine. Some people say, well, actually, it's not entirely a science. It's a lot of empirical things going on. But probably let's call it biomedical. Then I think science is perhaps a better expression. Now, I don't know who of you in this room knows, this is, in my view, the most famous doctor who exists. And looking around you, I see not as many people with gray hair as I have. So many of you probably wonder, who is he talking about? Never heard of this guy. This guy is, of course, Dr. McCoy, who from Star Trek, who had a fantastic device called the tricorder. And if you've ever seen these old episodes of Star Trek, this device was everything you needed in medicine, because you would wave it over the patient, and it would immediately tell you what's wrong with the patient and what you should do to cure the patient. And it would be, of course, fantastic to have exactly that also in reality, not only in science fiction. Now, if you look at actually what is reality about this, actually we're not that far away from this. So it was a tricorder was a device which would allow you to look into the human body. Well, actually, we can do this with all sorts of imaging techniques very well. So if you look, for example, at MRI imaging, I can really image the entire body in a lot of detail. I can look at certain aspects like the cardiovascular system or the brain. I can look at brain activation, can do fantastic things. So actually, we almost have that device, but it's not quite working. And I also wanted to highlight a bit perhaps why it actually is so difficult to get it to work in reality. And if you jump back to reality, now this might not always be everybody's greatest hero, but it's a guy who has made a lot of predictions, which not all of them turned out to be entirely correct. But Elon Musk said a couple of years ago, actually more than 10 years ago, we need 2 years to have self-driving cars. And a lot of people would probably argue, well, obviously that was a very silly prediction, but actually we're getting close. Now, this gentleman, Jeff Hinton, is of course a Nobel Prize winner. He made the prediction, well, radiologists will be obsolete in 5 years' time. And if you sort of think about that, probably also a wrong prediction, because reality looks much more like that, correct? So we're not quite there yet. And I also wanted to highlight a bit, we're moving in the right direction, not on the right side, but perhaps these predictions were wrong in terms of timescales, and also were wrong in how they perceive whether AI should replace humans or actually should work collaboratively with humans. So if you look at where AI is currently in medicine, you probably realize that actually most of the AI developments which are clinically adopted are in the field of radiology. Because in radiology, of course, what we do is we deal a lot with perception, and the radiologist does a lot of perceptual tasks. If you look at this paper, it's a bit outdated, but what's nice about this paper is the database it refers to is continuously updated. So you can check this link and you can see how many FDA-approved devices are around today. And you can see that these numbers are probably a bit outdated, but it's very slow. And I think it's also partly slow because we're probably sometimes asking the wrong questions about what AI can do. So if you, for example, think about, we've for a long time, and this is a point Jeff Hinton made, is try to replace a radiologist. We think about AI takes imaging and then performs automatically the diagnosis, tells you what's wrong with the patient. But actually what has worked so far much more successfully is actually AI transforming how we generate the images in the first place. Now you might say, well, is that very important? I would argue it is very important because medical imaging, for example, is a very scarce commodity. It involves devices which cost millions of euros, which are complicated to operate, and moreover, they're not widely available, and they're slow in how you get the imaging. So here, AI can make a huge transformation. And I just wanted to highlight that a bit with an example, which I think some of you can relate to. For example, if you do MRI imaging of the heart, one of the fundamental problems is you have a moving organ. You can't ask the patient to not breathe at all or stop their heartbeat. So you have to acquire data in a very complicated process with ECG gating, with respiratory gating, or you have to ask the patient to do breath holds. With AI, we can acquire data way faster than we could in the conventional setting. And that means we can make, for example, MRI imaging of the heart something which can almost happen in real time. And we can also do the same with, for example, brain imaging. Now here, what we're really doing is we're building AI into how the data is reconstructed, how the images are generated, and that is really transforming the field of radiology. So if you ever now go to a radiologist and ask them, do you use AI in your daily workflow? And if he or she would say no, then they're actually just not understanding what happens in these devices. Every modern MR scanner you now buy does exactly that. So this is really transformative. It's also transformative because it allows us to go away from this very expensive hardware to devices, for example, portable low-field, ultra-low-field MRI scanners, which really operate at a fraction of the cost and now can be deployed for applications which are not normally possible, for example, with conventional MRI, because you can actually bring these devices to the patient and you don't have to take the patient to the device. What you can also do is, of course, you can translate this to other modalities, for example, to ultrasound imaging. And you can now buy ultrasound probes, which you can plug into your smartphone and which you can use like a conventional ultrasound machine. And that means you can do ultrasound in principle at home, or you can almost go to the idea of here having, for example, wearable sensors which continuously do imaging monitoring as you wear, for example, a patch on your chest. So this is only really possible because we can take data which is not in the traditional sense, for example, will violate Nyquist sampling theorem and so on, where we can recover still clinically usable images. I also wanted to highlight a bit how you can use machine learning even perhaps more intelligently by combining modalities. So I've already told you that this MRI scanner is a very great modality, but it's very expensive. Now, if you are suspected of, if you have chest pain, you go to the emergency unit, they will not do immediately an MRI scan. They actually might not be able to do that for another 24 hours, correct? But what they will do immediately is an ECG. An ECG is super cheap, very easy to do, portable. Every GP can do that. A nurse can probably do the measurements for the ECG. But of course, it's way less rich information for clinical diagnosis than an MRI scan has. But what we can now do, we can use ideas, for example, from contrastive learning to sort of see is, well, is there some information hidden in the ECG signal which we can extract and sort of extrapolate to information which we normally only think we can see in the MRI? And we can actually do that. We can use contrastive learning techniques like SimClear or others, or you can use JEPA or other techniques to basically align the representations from cohorts for which you have paired data, MRI data and ECG data, and you can sort of learn a shared representation from these modalities. And then at inference time, you can predict some of the information which you might normally not be able to see from the ECG by using these type of models. And when you use these models at inference time, you can sort of, for example, extract from the ECG parameters like the ejection fraction of the heart, how big the heart is, how much blood the heart muscle can pump, and so on, directly from the ECG. And if you ask a human, can you do that? You have to admit they're never trained to do that because people think that's not a very sensible task, but they will really struggle to do this from the ECG. So why am I all telling you this? Because I think we're running into a very significant problem with healthcare. This is a statistic which shows you how much money you spend on the horizontal axis of our GDP on healthcare, and on the vertical axis, what's the outcome? What is life expectancy? And you see two countries which are sort of to the right side of this. US, obviously everybody knows, one of the most expensive healthcare systems. And if you look at sort of the performance, it's not great. It's way beyond, way lower than, for example, Japan, Norway, Switzerland. And if you look at Germany, well, actually we're moving very closely to the US. Our life expectancy currently is at least stagnating, it's not increasing, and the cost is rapidly increasing. So in a few years' time, we'll be much closer to the US than where we are now. So why am I telling you this, and what has this got to do with AI? I think one of the great opportunities we have is that we can sort of think about how AI can help us with diagnosis, with early detection, with therapy, and with monitoring of patients. But it also has the potential to move our spectrum of where we try to intervene or where we try to assess risk much more to the left-hand side. So if you really think about we want to do preventive, proactive medicine, then we need to really intervene at a much earlier point where we sort of really have the ability to modify disease. And for that, we need new biomarkers which help us, for example, detect parameters which might be related to aging, biological aging, which help us to identify risk prediction or help us to do risk prediction, and of course also give people some personalized health information. Because if I would tell you, well, prevention is a key, what you should do is avoid all of these things and do all of these things at the bottom. Now, I think everybody knows this, correct? And nobody, if you are surprised by this, well, sorry, I will not be able to help you, but on the other hand, how many of us actually do exactly that, correct? So the reason why we not do it is because I think these are not personalized recommendations. We all know these stories where you say, oh, I know somebody who has been smoking every day, and you know they died when they're 95. And likewise, you see, oh, this guy has been super sport active, had a heart attack with 55, correct? So what's really important is that we are able to personalize that. Now, this comes back to what I told you earlier about sort of the idea of a tricorder. Well, we now have a lot of modalities available, correct? Most of you will probably have a smartwatch or a smartphone, which is actually very accurate for recording what you do. We have omics technologies, we have handheld imaging, sensing technologies, and hopefully at some point in Germany we'll also have electronic healthcare records. So we can put all of this together, correct? And the idea is, perhaps if we have that, and if we have it from a large cohort, and I wanted to showcase here, for example, again, the UK Biobank, which is great because they have, for example, comprehensive imaging of over 100,000 subjects. They have for everybody. They have lifestyle, physical activity, genetics, and also in the UK, a link to clinical records. So what we can do with that is we can probably use that data, combine it with AI, and build personalized risk models. So we can, for example, analyze all of these images. We can extract automatically phenotypes of the heart, of the whole body, of the brain. These techniques now all exist, and they are really deployable. And what we can then do is we can, for example, say, well, in the first instance, let's identify potential correlations in the data. First of all, what we have done a couple of years ago is to, for example, even define reference values for what is normal, for example, in the heart across this massive population. And can we normalize it, for example, for male and female differently? Because, of course, male and female hearts are a different size, different pump functionality. And for example, of course, that also changes with age. So we can now sort of, for example, build personalized models, and we can identify correlations between what we see in the imaging and what we see, for example, with lifestyle, with cognitive function, with physical activity, and so on. So a lot of this is very similar to how you do genetic studies. These are sort of effectively phenome-wide association studies. You have to be careful how to interpret this because this is really correlation and not causation, but it's incredibly valuable. Now, if you also think about this, okay, how do we take this a step further? There are a couple of really exciting papers which have come out in the last couple of months on, for example, this Delphi paper, which tries to sort of predict disease risk based on your trajectory of previous diseases, or this paper from our group where we've tried to look at how we can use imaging to do the same. And then I wanted to highlight today something which we have done together with colleagues here from Helmholtz, where we sort of try to sort of see is, can we take that one step further, and can we build models which really give you your personal disease risk, and which you can query with different diseases, with different time horizons, and sort of also perhaps sort of simulate what happens if you change something in this. And this model, which hopefully we'll submit with our colleagues very soon, is quite interesting because it sort of enables you to take all this information, put it into effectively a sort of generative AI-based model in form of a transformer architecture, and then you can query it with natural language, but also with different diseases and different time horizons. So we are learning this shared representation where we take all these different modalities, map them into one space, and then you can, for example, see what is my stroke risk over a 12-year horizon, or what is my risk for emphysema over a 2-year horizon. And because we have a shared representation, which also aligns all these different diseases and the different data, you can actually exploit the correlations much better than if you build a model which only predicts your dementia risk and nothing else, correct? And so if you compare this, we've also, of course, also compared this to state-of-the-art models. The Delphi model I already showed you is this Nature paper from last year. That's a green line. What we can do at the moment with our model is, I think, way better. And that's super exciting because it really gives you a significant boost in performance for this personalized risk modeling. The other thing which I think is also interesting is that you can also use this to study disease clusters or population clusters, where you might sort of say, let me take this very big cohort of subjects and let me try to stratify it into subgroups or into clusters. Are there patterns which we can detect in the data which we cannot detect otherwise? And I think for those type of things, these representations are also incredibly useful. So I wanted to highlight at the end perhaps a couple of ideas where I think you take these models and you combine them with something where you have personal health agents. And I think you have already seen that, of course, everybody is now using large language models for, for your daily work. And you probably also have seen that a couple of months ago, health versions of these models have come out. So ChatGPT has now a health version. Claude has a model specifically designed for healthcare and medicine, and Google has released something similar. Now, actually, these things have come out, I think, in January for the first time, within a space of a week. So you see how much acceleration there is in the development of this. And likewise, you see almost every day now a paper, and I find this very telling, from tech companies like Google publishing Nature Medicine articles about how technology can transform medicine. So there is a lot of really interesting things happening in this space. One of the things which we also try to look at is, well, how good are these models? Can you really trust these models? Of course, that also depends whether they're aimed at clinicians or whether they're aimed at patients or consumers. I wanted to highlight a few, just how a couple of months or years ago, how people have traditionally evaluated these models. What they have done is they've taken an exam called the US medical licensing exam, where you need 60% to pass. So as a human, if you qualify in the US, you need to achieve 60%. If you look at this, actually, this is really old figures, but from 2022, ChatGPT was already able to outperform what was required here. And now if you chart the territory, I stopped at 24, but I think now we are almost reaching 100, correct? And the reason is, of course, these models probably also know what's in these questions by now, probably also in the training data set. But I think the other thing is they don't really simulate what happens in a clinical workflow. So I've just, because you might not really be familiar with the US medical licensing exam, and don't worry if you cannot really read this, I just want to highlight 3 elements. First of all, this US medical licensing exam always consists of multiple choice questions, correct? And it's very rare that you go to the emergency unit and say, oh, can you please tell me, do I have A, B, or C? So that's not really how this works. The second thing is, they give you all the information you need to make the diagnosis up front. And again, that's not something which happens, correct? You go to the clinician, they have to decide, do I need imaging, blood tests, whatever. And the third thing is, they use these classical symptoms where you basically, these are textbook style symptoms, correct? Where the patient is very articulate, describes exactly what symptoms they have. So this is really not good reflection. So what we've tried to develop is, for example, a benchmark where you really simulate the entire process of information gathering for the LLM. So they have to figure out, the LLM has to figure out what questions to ask the patient and so on. And then you can sort of develop a benchmark on which you can measure these techniques. And at least when we did this 2 years ago, sort of these models still had significant problems with quite a number of these aspects. And I still think if you test these models today, they're going to be better, but they're not going to solve these problems entirely. For example, they are very susceptible to the order of information you give to the model. So if you tell a model, I have high blood pressure and I'm a diabetic, and then you reverse the information, you say I'm diabetic, have high blood pressure, you might not get the same answer. And that's, of course, a big problem. So there are still a lot of problems with that, but you can also do a lot of interesting things with these models nevertheless. For example, you can combine different modalities. You can build vision language models, which can not only you can talk to, but you can talk to and you can show them clinical images. For example, we have done a lot of work in the area of ophthalmology where you basically might be able in the future to give opticians, which do a lot of imaging of the eye, the ability to do diagnosis in a optician's store rather than in a doctor's practice by, for example, saying, actually, you know what, I'm training a big vision language model for ophthalmology, for OCT images, by generating artificially question and answer pairs, which we have a way to do automatically. I don't want to go too much into details in this, but once you have generated these question answer pairs, you can then sort of say, well, actually show me what disease stage is visible in the image, or should I refer this patient to a clinician, to a specialist, and these are the following clinical guidelines. Are they met by this patient or not? So there's a lot of really exciting things you can do with that. So let me just conclude. I just want to highlight that from my point of view, the vision for AI is not only to do diagnosis, but actually to go to the prognosis of what will happen if you do certain interventions, because that will help us optimize these interventions. I think you also saw with these big models, we are able to cluster patients, we are able to stratify patients, and if you follow the mantra of personalized medicine, you can be able, or you hopefully will be able to stratify everybody in this room into groups of size 1, and therefore customize everything you do to that individual. And of course, you might also be able to use these models for prevention and for basically giving everybody a personal health agent. There are, of course, lots of other different tasks. Some of them are scientifically probably not super exciting, like administrative tasks in hospitals, but create a huge amount of value. So from my point of view, the risks of not using AI in healthcare far outweigh the risks of adopting AI in healthcare. So I think AI is the future of medicine. And it's probably also important to highlight that I don't think AI is there to replace doctors, but I think doctors who use AI will replace those who don't use AI. And I just wanted to finish with one slide, which also highlights that we have to think about how we train the next generation of clinicians, because if you sort of think about clinicians which now use AI, they have been trained before AI was really available. We have to sort of think about what will happen when they now use AI. Will they get way better, or are they going to be de-skilled? That's a big question. And also, what happens to the next generation of doctors? Do they ever achieve the same skill level because AI is doing all the hard work? So this is just some food for thought, and I just wanted to stop here. Thank you very much again for inviting me to give this talk, and also thanks, of course, to all our funders and to all the people in our group who did all the hard work. Thank you very much.